Welcome to my solution of the array-based binary search tree practice quiz. And so we need to write the insert item method for a binary search tree. And in this case, the binary search tree, we are storing the data, the tree itself, in an array. So the root will be the item at index 0, and then there's a function for calculating the children of each node, which is the parent's index times 2 plus 1 is the left child, and the right child is the parent's index times 2 plus 2. And to get the parent's index, you take the child's index, you subtract 1, and then you do integer division by 2. So let's get started. Here's my, oops, wrong one. Here's my text editor. So it is a array-based binary search tree. Author Cam Moore. Public class binary search tree. It's a generic search tree. We can store any object we want in it. Okay, it has a private array of e's that holds the tree data. So that's where we actually store the data. In the linked structure, we store it in nodes, and we have to keep track of the root. This is very similar to the array-based list or the array-based queue. We have the data stored in the array, not in linked structure, and we need our private comparator comp to do the sorting or the decision of what the order of the e's. So we now need to say insert the given item into the binary search tree at param item, the item to insert, at return true if the item is inserted, false if the item is already in the tree. We can't store more than one. Can't have duplicates in binary search trees. So public boolean insert e item. So we want to, I'm going to use a recursive way of doing this. You could do this with a while loop, but I'm going to do it. So what I'm going to do is I'm going to say return insert item and 0. It's the index of the root. Root of tree is at index equal 0. So recursive method to insert item into the tree. We now have two params. Param index, the index of the node we are checking for insertion. At return boolean, return true if item is inserted, false if item is already in the tree. And even if it's a private method, I still need to Java doc it. We Java doc all our methods. Item int index. Okay, so because it's an array and we're doing insert and that may grow the tree, we have to check if index is greater than or equal to the tree data.length. That means we're trying to insert one more thing into the tree. We need more space, so that doesn't mean that the tree is full, but we need to increase the length of the array. So I'll call my reallocate method. Similar to the array list or the array queue, reallocate, we increase the size of the array, copy all the values from the old array into the new array, and reassign it back to tree data. Okay, so now we know we have room. So now we want to say if tree data sub index is equal to null. So we're looking at an empty place. There's nothing here. So that is the base case, that I've traversed the tree to the right leaf of the right leaf of the tree. And so now I can say tree data sub index is equal to item, return true. Okay, so the else case is the item is we're looking at a node that has something already in it. So now we need to decide which way to go, left or right. Comp val is equal to comp dot compare item and tree data sub index. So we're going to do the comparison. If comp val is less than 0, that means we need to go, item is less than the index, we need to go left. So we now want to say we recurse, so insert item, and it's a left child, so that's 2 times index plus 1. That's the left child of index. 2 times the parent's index plus 1. And we need to return that value, right? We return the recursive. Else if comp value is greater than 0, that means we need to go to the right. We return insert item 2 times index plus 2, which is the right child. And so that's going to go down to the right. And then else we are looking at the item. The tree data index and item are the same, so it's already in the tree, we return false. And so, we got to make sure that we got room in the array up here. So we make sure that we have room in the array. If the node we're looking at, we're thinking is that, is null, then, not the node, if the item is null, that means it's empty, so therefore we can assign it, we return true. Else there's something in the, at the tree data, so now we need to compare to see whether we go left, right, or if it's already in the tree. And that's all we need to do. Now what's the big O? Big O of this is log n. Because each time we do the recursion, we are deciding whether we go left or right, which again divides the problem in half, Or the same thing, it's a binary tree. We're only going to traverse to the depth of a binary tree, and the depth of a binary tree is log n. So the big O of this method is log n because we're going to go down the tree. The only thing to really know about is, to think about and actually know, is that left child is 2 times parent index plus 1. Right child is 2 times parent index plus 2. And the parent is child index minus 1 div 2. So you do the, and it's the div is an integer division. So if we're looking at 3, it's 3 minus 1 is 2, div 2 is 1, so that is the parent of 3. Now if the child index is 4, you do the same thing. You say child 4 minus 1 is 3, div 2 is again still 1. So that's the right child of 1, and the left child was 3. So this is a integer division. So that's how we do it. So it's very simple. These 3 relationships are something you just have to know when you're doing trees, when you do an array. And I've got plenty of time left. So we can store the data in an array. We can use recursion. We could also have done this with a while loop to just keep going until either the tree data is null at index, or we can say that the comparison is equal to 0 because if we found the item. We just, each time in the loop, we need to make this if check to see if we need to grow the array. But I find it easier personally to do the recursive method because I don't have to figure out the looping. I just know that I'm going to make this very simple. If it's empty, I'm done and I return true. Else, I do the comparison, go left or go right, or it's already in the tree and I can stop. Thank you very much for your attention.